Okay, friends, let's walk you through a little bit of an explanation of why you can't always assume events are independent of each other. Now, some events are obviously independent. For example, rolling dice. If you roll a die, the next die roll doesn't remember what the previous die roll did. So things like the chance of rolling a 3 on a 6-sided die will always be 1 in 6. And the chance of rolling snake eyes on any pair of 2 dice is always going to be 1 in 36. Regardless of how many rolls happened before, the next roll is independent of the roll right before it. But how about another casino example? Let's talk about cards. Take a poker deck, 52 cards, 13 clubs, 13 hearts, 13 spades, 13 diamonds, shuffle them up, maybe not on your chest, maybe use a table, might be a touch easier. And then once you've got them all shuffled, deal 1 card off the top. In this case, we got a 7 of hearts. Now the chance that first card is going to be a heart is 25%. There's 52 cards in the deck, 13 of them are hearts. That's a quarter of the deck. Okay, so far, so good. What's the chance the next card that comes out of the deck is also going to be a heart? Well, it depends on what came out first. Assuming the first card was a heart, the chance the second card is also going to be a heart has to be 12 out of 51. Now, why 12 and why 51? Well, since you pull the card out and didn't put it back, there's only 51 cards left. And since you pulled a heart out and didn't put it back, there's only 12 hearts left. And hopefully this makes sense. It's going to be harder to get the second heart than the first one because you removed 1 heart from the deck. Now let's see how this applies to this project's math. What is the chance that the first 2 cards you deal off the top of this deck are going to be hearts? Well, if we use our multiplication idea and the 2 probabilities we just established, it's going to be about 5.9%. You take the 13 out of 52, which is the chance of getting that first heart, times the 12 out of 51, which is the chance of getting that second heart. Taken together, that's about 5.9%. That's what happens if you treat the 2 events dependently. What if you treat them independently? Well, that would just mean that the probability of getting hearts would not be changed between the first and second card. So in other words, 13 out of 52 for both. Multiplying those together, you get about 6.25%. And some of you might be looking at these 2 numbers going, wait a minute, are they really that different? Well, the answer, like so many things in life, is it depends. For example, I've made this little Excel spreadsheet to kind of model what happens as we keep drawing cards off the deck. What happens if you treat the probabilities of successive hearts in a row dependently or independently? Dependently meaning that we actually take into consideration that the hearts coming out are affecting later probabilities, independently pretending they don't affect them at all. So looking at this little T-table, the first 2 rows you've already seen before. The chance of 1 heart coming off the top of a deck is 25%, no matter whether you treat it dependently or independently, because there's only one card coming off. It's the second card where the numbers start to change. So yeah, there's not much of a difference between 6.3% and 5.9%. But look what happens as we start taking more and more cards off. 3 hearts, 4 hearts, 5 hearts. Now, the real, I think, tell is when you start comparing the 2 probabilities of independent versus dependent. That's what I've done over here in this column. I put a probability offness factor. So what I did was I took the independent probability and divided it by the dependent probability. The number that's in this column tells you how much off the independent probability is from the true correct dependent probability. Now, up to about 5 cards, you're only off by a factor of about 2. But the more cards you draw, look what happens to that probability off factor. It gets worse and worse and worse. And some of this worsening offness can be attributed to the fact that these probabilities down low are really, really small. So even though they might be close subtractively, they're very, very far away multiplicatively. But the fact of the matter is, treating these independently is incorrect. These are dependent probabilities. Okay, everybody, I don't want you freaking out about this stuff. Some of you, I can feel you through the camera like, oh my God, dependent, independent, I don't understand. You're giving me odds of the rule. I don't want you getting super worked up at this point in the game of not knowing whether or not events are independent or dependent. You're just learning about it now. I'm just trying to put it on your radar so that you don't assume everything in the world is independent, because that can't possibly be true. Think about your life. Your life is the sum total of the experiences you've had. An experience back here in your youth most likely impacted your experiences moving forward. That's the definition of dependent events, right? Very little in the world can be provably independent. That's just a fact of the matter. Yeah, dice, sure. Dice or slot machines, those are independent, sure. But as we just saw, cards, something as simple as cards, are dependent. And did you ever wonder about this? Card counting happens. Dice counting doesn't happen. And that's quite simple. Because with card counting, seeing the cards that are coming out gives you information about which cards are left in the deck. A die doesn't do that. So, long story short, lots of things in the world involve dependent events. Long story longer, we'll deal with bridging the gap more kind of concretely between dependent and independent events when we get into the binomial distribution. So don't freak out. I got you.